Alright, so in this short video we are going to review a few aspects that are going to be very useful for the upcoming section, in which is factoring polynomials over the complex field of numbers. So in this case, let's review the difference of squares. So we know that the difference of squares are that one factors over the real numbers. Right, let's write down the formula for the difference of squares when we have something like that's the wrong number, a squared minus b squared equals a plus b times a minus b. Let me make up a few examples here. For example, x squared minus 36. So 1 plus 1 minus, or 1 minus 1 plus, the order doesn't matter. X plus 6, x minus 6. Something like 4x squared minus 25. That's going to be some plus, some minus. Okay, the quantity whose square is 4x squared, that's 2x. And the quantity whose square is 25, that's 5. Okay, can we do this with numbers that are not perfect square? Perhaps yes and B. And we have already done some of those if you remember from the previous section, something like x squared minus 5, for example. Okay, so even though that 5 is not a perfect square, we can treat it in a way as we can look for the quantity whose square is 5, and in this case it's negative. It is the square root of 5 and the negative square root of 5. Okay, so we might need to have those in mind. Now, what about the sum of squares? So, when you are in the intermediate algebra course, you are taught that the sum of squares, the sum of two perfect squares, it's a prime polynomial. However, if we extend this to the imaginary field of numbers, we're going to have a result that is very similar to that of the previous a plus b. Notice the space I'm going to leave, a minus b. So I'm going to leave an I here and an I there. So as an example, I'm going to have this x squared plus 49. So I'm going to factor this. 1 plus, 1 minus, x, all right, x and x, and plus 7i and minus 7i. I'm going to do the same for something like, I don't know, maybe 9x squared plus 64. Why not? 9x squared plus 64. So the quantity whose square is 9x squared is 3x plus the square root of 64, which is 8, but in this case 8i. And on the other hand, 3x minus 8i. Okay. Can we have something like a term that is not a perfect square? Why not? X squared plus, I don't know, let me make something up. Plus 11. X squared plus 11. So in this case, I'm going to have the product of two conjugate binomials, 1 plus, 1 minus. So the quantity whose squared is x squared is x, and the quantity whose squared is 11 is the square root of 11. However, because in this case it's a sum, I'm going to add an I multiplying the radical. Same here, I times square root of 11. Okay. Now let's do the backwards of this a little bit. For the backwards of that, let me make something up. X plus 7, x minus 7, and 3x minus 11, 3x plus 11, and then x minus the square root of 13 times the square root of x plus the square root of 13. So in this case, all we do is the square of the first term minus the square root of the second term, which in this case the square root of 7 is 49. The square of the first term on each binomial, which is 3x, so the square of 3x is 9x squared, and the square of 11, which is 121. And finally, the square root of x in this case, which is x squared, and the square root of 13, in this case is just 13. Okay. What about with complex numbers? I mean, with imaginary numbers. So let's see. Something like x plus 6i, x minus 6i. Keep in mind that in this case we squared the first term, which is x squared, and we squared the number, which is 6, which is going to give us a 36, but in this case we put a plus in between because of the presence of those imaginary numbers. Okay, and then what else? For example, x plus I root of 19 times x minus I root of 19. So in this case, this is x squared plus the square root of 19 quantity squared, the root with the radical and the root with the power cancel, and we get x squared plus 19. Of course, if you want to do the foiling of this, you should get this. However, if you keep in mind both of these formulas, that's going to simplify a lot all the work that is going to be required. This one could take us even 20-25 seconds to do it with the foiling. However, keeping in mind the form and the concept of factoring a sum of squares will make these calculations to take a lot less than usual. Now we're gonna run into a situation in which we are not just gonna have real number and imaginary number, but actually complex numbers. For example, like in this case, let me make something up. Something like x minus 1 minus I, and x minus 1 plus I. All right. So in this case, we will need to find a polynomial whose factor form is this product of two trinomials, because this is 1, 2, 3 terms, 1, 2, 3 terms. Now, you might be thinking this is going to be a hell to simplify it. And yes, if you do it by foiling, it's going to be 1, 2, 3, 1, 2, 3, and 1, 2, 3. You will need to make 9 multiplications. However, in this case, I'm going to take a totally different approach. So in this case, I'm going to consider this as x minus 1, x minus 1 as one factor, as one term, as one single term instead of being two terms. And I'm going to consider the factor. Let me find another marker here, a different color. Then I'm gonna use this. I don't want to use the blue one. I'm gonna use this color. Hopefully it's visible. And then this is gonna be another term. Okay. So I'm going to make this look like a difference of squares. Wait a minute. Can we make that? Of course, we're gonna do that. So in this case, think of this as having your a minus b times a plus b. And this will be the factor form of a difference of squares, a squared minus b squared. Okay. So I'm going to do the following. I'm going to square minus squared. Okay. Let's see. So it's going to be x minus 1 and in this case it's going to be simply I. So in this case, recall what we did in the review session in which we expanded the perfect square binomials. So in this case, I'm going to have for this guy x squared minus 2x plus 1. And what do we know about I squared? I squared, keep in mind that's negative 1. And then when we add this, we're going to have plus 1 and then 1 plus 1. That's going to give us x squared minus 2x plus 2. So that's one example. All right. But again, if you want to go through the painful process of foiling this, doing this process 9 times, it's up to you. It's going to take you forever. However, I would take advantage of the difference of squares formula. All right, I'm going to make another example here because why not? So something a little bit more complicated, and x minus let me actually make this x plus 3 minus 4i times x plus 3 plus 4i. All right, and I'm going to do the exact same thing I did in the previous example. I'm going to highlight this, and I'm going to call this my a, and I'm going to highlight this guy, the 4i, and I'm going to make that my b. So again, let me label this. This is a minus b times a plus b. And the result will be again a difference of squares. All right. So I'm going to square x plus 3 minus 4i squared. Okay. So this will be a perfect square trinomial, x squared plus 6x plus 9 minus 4 squared, which is 16. But this I squared is going to be a negative 1. Okay. This guy right here, the I squared becomes a negative 1, and the 4 squared is 16. So this is going to be a plus 16. So 16 plus 9, that's going to give me x plus 6, x squared plus 6x plus 9 plus 16, that's 25. All right. So more often than not, especially in the following section, we're going to run into situations like this in which again we are going to have the product of two binomials in which the constant term will be a complex number, not just a real number like this or a simply imaginary number. So in this case, it's going to be a combination of all of them. And yes, your first thinking will be, oh, foil this and do this process 9 times. Yes, it's doable. You will be able to do it. However, it's going to take forever. So I would take advantage again of this difference of squares form. Okay, so now after looking at these examples, we're ready for the next section.